Hey everybody, now we're going to do the second type of balancing where we have acid catalyzed reactions. So you may want to write down these steps because I'm going to use the example in the next slide to do the to kind of show how you do this. If you're one of these people that needs to have like a stepwise progression, there it is. So let's go to here though. Okay. So let's do this. So we have the, it looks like the vanadite ion. I'm not sure exactly how to pronounce it. But whatever, you have this zinc going to the hypovanadite ion to zinc 2+. Okay, I'm not an inorganic chemist, so I'm not sure exactly what those things are, but we'll do it. Okay. So, step 1, or step A, okay, I'll flip back and forth between these things here. Okay, step A, split into the half reactions. Hey, I must have hit that. Okay, so let's split it into the half reaction. I know that zinc, okay, zinc is going to I know that zinc is going to react to form zinc 2+. I'm going to leave the states off, okay? And I also know that that's the oxidation half reaction. Now, if this is the oxidation half reaction, this guy must be the reduction half reaction, okay? So, just to show that, oxygen is a 2-. You want the charge to be 1+ overall. So that must be that vanadium has a 5+ charge here. 2 times 2 is 4-. You need an extra plus charge. Okay, and so this is 2-. There's only one of them, but you want the 2+, so this is going to go to 4+. Okay, so I know that the reduction half reaction is VO2 plus reacts to form VO2+. Okay, and I kind of label these things just to make it, I don't know, more clear in my mind. Okay, so then the first thing to do is to, once we do that, is to balance all the non-hydrogen and oxygen atoms. Okay, so here we have one zinc, here we have one zinc. Done. Okay, here we have one vanadium, here we have one vanadium. Done. That's balanced, addressed, life is good. Now what we want to do is we want to balance the oxygens using water. And this is kind of the funny thing, is because you may have looked at this and said, well, how the heck can we have only two oxygens here but only one oxygen there? How does that even work? Well, this is where redox can get fun when we're doing acid and base catalyzed reactions, because how many oxygens do we have here? 2. So the next step, let me just highlight, right? Balance all oxygens using water. Okay, so we're going to do that. We're going to say O2, so we need an extra oxygen, so we're going to do plus H2O. Now the question is, that I always ask, is where does that water come from? Well, all the reactions are done in aqueous solutions, so there's always an excess of water hanging around to participate in redox reactions. Okay, so that's never a problem. Okay, but by doing that, now we've added hydrogen to the mix, and that's bad. But this is an acid catalyzed reaction. This is acid catalyzed. Okay, so if it's acid catalyzed, we probably should be able to use H+, and that's where this comes from. If you look back here, the next step is any hydrogens balancing using the hydrogen ion. Okay, so here, because I have 2 H+, I'm going to put, or 2 hydrogens, I'm going to put 2 H+ in here. Okay, and so that's how you balance using the water. That's the mechanics of the balancing using water. Now the rest is going to be similar to what what it looks like when we have uncatalyzed reactions. Okay, we want to do a charge balance. Okay, and by doing a charge balance, let's see, here is 2 plus and a plus. So this side, okay, and I can do it in red, this side is 3 plus and this side is only 2 plus. Okay, so that means that this side needs 1 electron. 1 electron. Okay, and now does that make sense? What is reduction? Okay, gaining electrons reduction. And yep, that makes perfect sense because your electron is on the reactant side. And so now for zinc, 2 electrons need to be given off because this is 0, this is 2 plus, so you want this to be 2 minus to cancel out the 2 plus. This is the charge balancing. Okay. Now the next step is to make sure that the number of electrons cancels. So how many electrons do we have here? 2. How many electrons do we need? We need 2. So by doing that, this lets us perform the balanced redox reaction. Okay, this lets chemistry perform the balanced redox reaction. We have 2 electrons being lost in the oxidation half reaction. Those 2 electrons have to go someplace. Where do those 2 electrons go? They go down to the reduction half reaction. So if those 2 electrons are going from the oxidation half reaction down to the reduction half reaction, there has to be 2 electrons in that part of the reaction, in the reduction. So that's why we take this and we multiply it by 2. Okay. Now, we can't just multiply the number of electrons by 2 because that's going to throw our balance off. That's why we multiply the whole reaction. Okay. So 2 times all of this. So what ends up happening is the number of electrons cancels, but this then becomes 4 and 2. And so what we're going to do is we're going to recombine this. Okay. So we're going to get Zn solid plus, and now we get plus 4H plus aqueous. Keep that in mind that that's aqueous. Plus 2, because it's 2, VO2 plus, and that's aqueous. Okay, right there. Reacts to form, okay, Zn2 plus 2 VO2 plus 2H2O. Now, that's a lot of craziness that's going on there, but there's a couple of checks we can do. Okay, the best check to do when you're doing this is to check the charge balance of the reaction. Okay, what's the charge balance on this side? This is 4 plus and this is 2 plus, so this is 6 plus here. 2 plus, and then 2 times 2 plus is 6 plus. 6 plus equals 6 plus. It's got to be balanced. And I can assure you that if you go through this, the atoms are going to be balanced as well. Okay, so there's balancing an acid-catalyzed reaction. Have a great day.